Good morning, everybody. My name is Madison Deal with AIST, and I want to thank you all for joining us today for our first decarbonization webinar of 2026, Introduction to Sustainable Steelmaking. We had a group of 9 industry experts and members of our decarbonization subcommittee come together to create this information-packed webinar that will introduce you to the global importance of steel, explore integrated and electric arc furnace steelmaking pathways, highlight the key challenges in reducing emissions and managing resources, and conclude with both current pain points and future innovations driving toward greener and more resilient steel manufacturing. Before we begin, I want to take a moment to thank today's webinar sponsor, Big River Steel. We really appreciate your involvement, and we will also be our sponsor for March. Couple guidelines to review. AIST's antitrust guidelines, first and foremost, you can see here on the screen. Just keep in mind, this is a technical presentation. We're focused on knowledge sharing. So please, no discussions or questions related to pricing or any competitively sensitive information. As well as AIST's anti-harassment policy, we want to keep this a safe and harassment-free environment for all parties involved. Any type of harassing behavior will be immediately put to a stop. Some guidelines for the webinar. Your audio as attendees has been disabled, but you will be able to submit questions via the Q&A feature in Zoom throughout the broadcast. That should be a feature on the bottom of your Zoom screen. So please submit questions throughout. Some of the questions submitted you'll see answered via chat, and the other questions that appear in the chat but have not been addressed will have a live Q&A at the end of all of the presentations today. Now, this webinar is being recorded and it will be available for your review afterwards on AIST's website, along with all previous webinars that the Decarbonization Subcommittee has done. So please no photos or recordings of the presentations while we're doing it. And if you do have any technical difficulties throughout the webinar, please contact training@aist.org. Now, without further ado, I would like to introduce today's moderators. First, Dr. Felix Versbach of the Badische Group. He is the chair of the Decarbonization Committee, and David Marshall of the Performance Improvement Incorporated, who is the founder of the Decarbonization Committee.
Yes, Madison, thank you very much for this nice introduction, and I'm very happy that we have this wonderful webinar today. So shout out to everybody who joins us today. We're very happy that you're here. Before we start with introducing the first presentation of a few, just the information, there will be a poll coming up saying what is your greatest concern about steel sustainability. So this will come up on your side. You can answer that throughout the webinar, and at the end we will see the results of this webinar. I think you must be able to see it now. You don't have to click it right now. Listen to the presentations, put it aside, and it will be interesting to see what your opinion will be. Having that said, now I'm happy to introduce the next presentation. Could please have me to click for the next slide. So this presentation's title, you can see on the left-hand side, is the role of steel in the world. So this is a global introduction to this topic. It will be presented by Joe Mori from Mori Industrial Consulting, who is in the industry already since 28 years. And he was supporting in the creation of this presentation by Brian Black from SMS Group, who's Vice President for Coke and Iron Processes. Having that said, thank you very much at this moment, and the stage is yours, Joe.
Hey, Joe, I think you still might be on mute.
So, Joe, slide scrolling works. You seem to be unmuted. We don't see you yet, but the stage is yours.
You're going to have to help me with my camera somehow. It's not... Apologies here. Okay. All right, I'm just working through this here. Okay, here we go. We will start now. Okay, thanks a lot for joining, everybody. We have 78 attendees. This is so awesome. We have a worldwide a group of people here, and so I'm very excited to present this this part of the webinar. You know, this is a very difficult topic that we're trying to tackle here. Steel sustainability means keeping steel's essential role in the world and dramatically cutting its environmental impact. Steel is one of the most important things that we manufacture in the world. It underpins our entire society and global development. It's important for everything, including security, our infrastructure, almost anything that we do. But just despite this importance, steelmaking remains one of the largest industrial sources of emissions. It's 7 to 9% of the global greenhouse gas emissions. So you can imagine that when people want to cut greenhouse gas emissions, that steel would be such a dramatic target. But tackling this is not easy. We have to strike a balance. We have to reduce greenhouse gas emissions. And we also need to ensure that steel is available for everyone so they can grow their economies and also push any type of project that they want to do. So I want to talk just real quick about why steel is foundational. It's for national security. It's not only for, it's for tanks and ships and guns and just all the things that go into national security. So when we say it's for national security, we talk about that, but it's also because it underpins our entire infrastructure of things that that happen in each and every country. Bridges, rail systems, and everything that just kind of puts things together. It's important for how we get from one place to the other, how we ship goods from one place to the other. Automotive, trucking, rail logistics, and shipping. None of this could be done without steel. Steel is energy, also energy. So this entire energy transition to try to make reduce greenhouse gas reduction, it's going to be rooted in steel. The foundations, the towers, the piping. Think about all these things that are going into these projects. It's all going to be rooted in steel. And so, yes, even we have made progress in reducing greenhouse gas reduction. You can see here, we've gone from back in 1960, we were at 2.4 tons per ton of CO2, and we're all the way down to a little over 1.90. And some of this was done just through sheer economics. Steel scrap became plentiful as our society started recycling and tearing things down and reusing things. And the advent of the EAF helped kind of bring this into light. And this is what's really driven a lot of this efficiency here. And the blast furnace and other processes have also become more efficient. At the same time, we improved our greenhouse gas efficiency. The use of steel has actually also increased. So now our total amount of emissions have increased dramatically with the usage of steel. So the end result is changing steel efficiency is not enough. We have to dramatically do it. And the most important pathway is iron making, which is the the #1 greenhouse gas emitter in all of steel making. It's key as it's the most energy intensive step. Right now, not everybody can go to electricity. We'll just talk about that real quick. As blast furnaces are shut down in the Western countries, and we're trying to lean on electricity as a potential source of making clean steel. All places aren't able to do that. So in Asia, for instance, they rely on a lot of coal, and scrap is a lot less plentiful there. So they're still building blast furnaces there. Steelmakers need options, but we don't need mandates. So talking about again about steel recycling, it's nearly 100% recyclable. You can use a steel beam over and over and over again, just remelt it and remake it. The fact that steel is magnetic makes it super easy to separate, so it improves the recovery and lowering landfill. In North America, I was really surprised to see this, that we have an over 80% recycling rate. It's one of the highest of any material, so that just kind of strikes to show you that we can recycle steel. And when you recycle steel, you save approximately 74% energy and approximately 60% of the greenhouse gas emissions. While this recycling piece is super important, the world still needs clean, high purity iron units, or we won't be able to make some of the high quality steels that we want to make. Okay, I'm going to kind of transition to the next group and talk about the DRI and the blast furnaces. These are the two biggest forms of iron making that I said that was so critical into reducing the greenhouse gas emissions of steel. And DRI, the positives, they're typically alloy free. They're an efficient use of top gas, much more than the iron making. It's 33% lower greenhouse gas when you make it with natural gas. You can almost get to zero with hydrogen, especially if with your renewables are being used, and you can export that because it's already a solid form. Although generally it retains oxides, it's harder to melt in the EAF, and it's more expensive without low-priced fuel. So they really rely on that. The blast furnaces, they're alloy-free. They're typically less expensive. They're easier to melt in solid form, and they automatically remove the gangue, which is an important point. It's hard to export that because you need to solidify iron, and it's generally more capital intensive. So integrated steelmakers have a lot of equipment that are on the ground already. The big negative is it's higher in greenhouse gas intensity. So we'll switch off and to our next presentation. Thanks a lot.
Thanks, Joe and Brian, for an excellent presentation. I think we can now understand that steel is critical. However, it's not an easy business to be in, as we've seen from all the mergers, acquisitions, and shutdowns. Cash is king, and that's what counts. Remember that throughout all the presentations. So our next section is looking at how we make steel. Thank you to Mike Grant, consultant, Chris Pistorius from Carnegie Mellon, Brian Black from SMS, and Mike will make the presentation. Go ahead, Mike, please.
Thank you, David. I'm just going to follow up on Joe's presentation. I'm going to, if I can advance it, let's see what's happening here. There we go. So basically, I'm going to talk about a little bit more detail on what the processes for making steel are. And I would like to direct your attention to the World Steel Association website, which has done an excellent job in preparing this illustration of the steelmaking process. And you can see it starts on the left-hand side, the list of typical raw materials and the preparation, going on to the different iron making, two different iron making processes, and finally about the two steel making, classical BOF and the electric arc furnace. And I'm going to break this presentation into two forms. I'm going to talk about iron making, and I'm just going to give you some background on the way steel is made as best I can do in 15 minutes. And I'm going to start with iron making. And iron making is basically the blast furnace, which is the classical method. It's been made for centuries with a blast furnace. And more recently, direct reduced iron, which is a natural gas based. And Joe introduced those earlier. So first of all, let's look at the growth of steel production in the world. And up until about 2000, the world produced less than 1 billion tons, around 800 million. And most of that was made with the classical blast furnace, basic oxygen furnace processes. In about 1980, a new process was developed, direct reduced iron, primarily gas-based, natural gas-based process. And this started to grow because it provided an alternative to steel making in countries where natural gas is relatively inexpensive. But starting around 2000, we saw exponential growth in steel making, primarily still, even though these are the two most emitting processes in steel making. The growth was primarily in the blast furnace BOF process. So first of all, iron making starts with iron ore. And I'm going to use the North American example. This beautiful picture on the left is a picture of taconite. This is the primary form of iron ore that is mined in North America. You see the sedimentary layers that are within the rock. The dark layers are magnetite, which is Fe3O4, and the red layers are primarily silicon oxide, SiO2. Overall, it's about 30% iron content, and we liberate this iron ore by grinding it really fine. So by grinding it to very fine particles, we can separate the silicon oxide from the magnetite and separate it using magnetic separation. The magnetite is actually magnetic, so it can be picked up with a magnet. And then there are other forms of separation. Froth flotation. It's a liquid a way to separate the different minerals. If we look at the flow sheet for taconite ore processing, we have grinding, flotation. We separate the valuable magnetite material as best we can. To do this, we have to grind it very fine, around 50 microns. And this, of course, is not suitable for the process. So we have to then agglomerate it again. So we add a binder. That's typically a type of clay. We pack it together in little balls, and these become sinter or pellets, as you can see pellets in the photograph here. And we need to do this because these particles, we need to be able to pass a lot of reducing gas through the blast furnace or the DRI reactor in order to be able to make the process function. So with these two processes, of course, we can divide by the types of CO2 emissions that we're concerned about. Probably you all know what these are already, but I'll just highlight them quickly. Scope 1, those are the CO2 emissions that are directly emitted from the process that we're working with. So the blast furnace, what comes out the stack of the blast furnace, or what comes out the stack of the DRI reactor. The CO2 release, the direct emissions, are Scope 1. Scope 2, if the process consumes electricity, for example, and that electricity is made by burning fossil fuels, that electricity is going to be a source of CO2. We need to add that to the Scope 1 emissions to characterize our overall impact on the on the emissions of CO2 for the steel process. And then there are scope 3, less clear, but an example of this would be the emissions created upstream in producing for example, iron ore pellets or producing coke, assuming that coke is not produced at the steel mill site itself. This is a basic diagram of a blast furnace. We charge about 1,600 kilograms of pellets, iron ore pellets or sinter, into the top of the furnace, along with some flux to make a slag and about 450 kilograms of coke. These form a packed bed in which we blow gas from the bottom. So we're blowing in hot air up to 1,300 degrees C and some oxygen. Typically averages about 40 normal cubic meters of oxygen per ton of iron. We blow these in, it burns coke at the bottom, makes carbon monoxide. This carbon monoxide reacts with the iron oxide pellets to produce metallic iron. The energy consumption of this, okay, it's a bit slow. The energy consumption of the overall process, blast furnace process, is about 3.6 megawatt hours per ton of hot metal. And the CO2 intensity, so this process emits 1,400, 1,500 kilograms of CO2 per ton of liquid pig iron that is produced, that is tapped out of the furnace. And therefore, the blast furnace produces actually more mass of CO2 than it does iron. Iron is the product, of course, we want to process into steel, and we're actually making more CO2 than we are iron. The hot metal comes out at about 1,500 degrees C, along with a slag, which captures many of the impurities like sulfur and other things. Now, this is an example of gas-based direct reduction. There's two types, the energy iron here, but there's also the Midrex gas-based technology. Both of those rely on natural gas, and natural gas is reformed by reacting. Well, methane is natural gas is mostly methane. We react it with both water, steam, and CO2 to make our reducing gas. And reducing gas is CO and hydrogen. These react with the iron oxide to produce metallic iron. You can see the two diagrams or two equations here. A less significant but important reaction is the carbonization of the DRI itself. So in many cases, the metallic iron reacts with the natural gas itself to produce iron carbide, which provides a useful source of carbon in the DRI product for the electric arc furnace that's going to melt it afterwards. Just a very simple mass balance of the DRI process. We're charging in about a little less weight of iron ore because it's pure. It's got less gangue material. We charge about 1.3 tons of iron ore into the top of the DRI reactor. We reform about 190 kilograms of natural gas. Of course, we need to power all of these things with about 100 kilowatt hours per ton of electricity, and we get about 390 kilograms per ton of DRI out the top of the DRI reactor. And this produces a DRI with a composition somewhere around 85% metallic iron, and it's and some residual iron oxide because it's impractical to reduce all of the iron oxide to 100%. A key quality parameter is metallization, and metallization is defined as the fraction of total iron in the DRI that's in metallic form. And this is important because the higher the metallization, the more friendly it is for use in the electric arc furnace, the more easy it is to melt, and the less power consumption. And the energy consumption for a ton of DRI is somewhere around 2.8 megawatt hours per ton. And the CO2 intensity, depending on the other factors, so the process itself makes around 400 kilograms of CO2. If the electricity and some other products also emit CO2, that can be bring the total to more than 600 kilograms of CO2 per ton of metallic iron. So it is a significant source of emissions. Now I'll bring back this great diagram again. I'm going to talk now a little bit about steel making. We have the two main processes for producing steel. The classical basic oxygen furnace, which refines blast furnace hot metal into high quality steel. And then we have the more recent but becoming classic electric arc furnace, which melts mainly scrap, but also melts DRI to produce steel that is often maybe not quite as high quality as the basic oxygen furnace, but it's fast approaching. So BOF steel making, classical example, this has been the primary way of making steel since the 50s. It's defined, BOF is basic oxygen furnace, and in some parts of the world, like here in Europe, it's often called LD furnace, which stands for Linz-Donawitz, the two cities in Austria where Voestalpine invented the process. Basically, what we're doing is we're blowing in high velocity oxygen at supersonic speeds to refine a mixture of high carbon liquid metal from 4.5 weight% carbon down to between 0.05 weight% and 1 weight%. And we're blowing this down with oxygen. The charge typically consists of between 75 and 90% liquid pig iron and 10 and 25% scrap. The primary reactions that take place, the carbon in the hot metal from the blast furnace is burned with supersonic oxygen. It makes CO. And then in any case, that CO is burned as a fuel with oxygen, primarily in air, to produce CO2. And this is where the emissions come from. We get energy from this reaction with carbon, and we also burn out some residual elements such as silicon, manganese, chromium, aluminum, and phosphorus. And the combustion of these products produce these oxides, which are removed in the slag, and this combustion process gives energy to the process. So in total, BOF is responsible for between 150 and 200 kilograms of direct CO2 emissions, or scope 1 emissions, per ton of steel. This is a basic oxygen furnace. It's not a really complicated vessel. The scrap and the hot metal are charged into the bottle-like vessel. This lance delivers supersonic oxygen at Mach 2 times the speed of sound, to vigorously burn out the carbon and the residual elements from the process. So that's the basic oxygen furnace, the classical steelmaking process. The electric arc furnace steelmaking is becoming more and more common, especially because it is much more friendly from a CO2 footprint point of view. In the US, 72% of the steel made in the US is from the electric arc furnace. It's designed primarily as a scrap recycler. So as Joe mentioned, steel is virtually 100% recyclable, and recycling scrap can be melted and made into new and usable steel. It's done so using an electric arc that produces a plasma of roughly 10,000 degrees C, rapidly melts the scrap into a liquid steel, produces and uses about more than 100 megawatts for the typical 150-ton batch of steel that's produced. This power is delivered through graphite electrodes into the bath. When we need higher quality steel, we dilute the impurities. Scrap has a lot of impurities. We dilute those impurities with so-called virgin pig iron, which is DRI, or sometimes solid pig iron from the blast furnace. This is charged, it's pure iron, charged to dilute the impurities from scrap. And this can be charged typically as high as in quantities up to 50%. Oxygen is injected into the bath, just like in the BOF. But we also use oxy-fuel natural gas burners to heat the cold spots in the electric arc furnace. And these burners also inject supersonic oxygen into the steel itself to assist in melting the scrap in the DRI. We inject a little bit of carbon. This is used to treat the slag, produce what we call a foamy slag. It's a slag treatment process. But typically, compared to the basic oxygen furnace, the emissions, the Scope 1 emissions, are quite low, 150 kilograms per ton. Scope 2, though, if the electricity for melting the steel is produced by burning fossil fuels, we can suddenly see a rapid rise in the overall emissions to above 600 kilograms per ton. Just a quick energy balance. We categorize the electric arc furnace by how much power it uses. So, I mean, a typical energy consumption, electrical energy consumption, is about 450 kilowatt hours per ton. And this is the amount that determines, the productivity of the electric arc furnace. How fast we can deliver that electricity means it determines the speed at which we can produce a batch of steel. Other energy contributors, though, are the reactions involving oxygen. So all of these impurities that are burned out of the steel during the processing produce energy. So the bath reactions, in this case, contribute almost 100 kilowatt hours per ton. We have burners that could contribute 50 kilowatt hours per ton, and some of the other reactions. These contributions are denoted by a negative sign to show that these are energy contributions. So we're delivering 450 kilowatt hours per ton electrical energy. 47% of the total input is actually chemical from all of these reactions that take place. So it's called an electric arc furnace, but the chemical energy delivered is a key role for the production. And so the total energy could be, in this case, 850 kilowatt hours of total energy per ton of steel. And at last, this is a picture of the DRI process, or the electric arc furnace process. You can see these graphite electrodes here delivering enormous amounts of power, melting the scrap that's inside this furnace. Scrap is charged in the top. This roof actually swings open to allow the scrap to go in. We melt with the electrical energy. The slag, which takes care of the impurities, comes out this door. This door opens up and the slag rolls out. And this is basically the process. And so this concludes my presentation. I hope this brief description was helped you understand better the process. Thank you very much.
Mike, thank you very much for your great presentation. Now we will go to the third presentation of today's webinar, Key Pain Points of Steelmaking Sustainability. So this will be presented by Sarah Hornby from Global Strategic Solutions, who did a lot of consultancy work on EAF and sustainability. And she was supported by Ian Sutherland, who is also in the call, from System Zero Consulting, and our moderator, David Marshall. So having that said, I do not want to waste your time with introduction and give you more time with Sarah. So Sarah, stage is yours.
Thanks very much, Felix, for that introduction. As most of the audience might know, the original quote-unquote sustainable steel processing was going to be a conversion from blast furnaces to electric arc furnaces run with green energy and green hydrogen in place of the natural gas in the DRI plants. So I'm going to look at some of the key pain points that are involved in this. Hopefully it will move.
I think I'm still in control.
Oh, Madison? Basically, I'm going to look at some of the key pain points in terms of the sustainable steelmaking. It's predominantly directed at the DRI processing, but also includes some of the new processes that are coming forward. And can we? No.
All right, Sarah, you should have control. Try using your arrow keys.
I'm trying. Not working. There we go. Okay, so the first point that we've presenting here is an overambitious project objectives. Basically, we've seen multiple times the following announcement of a large-scale decarbonization project, there's a lack of progress, and then eventually the project is abandoned. There are a number of reasons why this occurs, and I'm going to expand upon that in the short time that we have. But the common thread is basically the project stakeholders' expectations are unrealistic when viewed in the lens of basically real world complexities and constraints. So the first is an insufficient project scope definition. This often occurs when the focus of the project is given to a core piece of technology, for example, the electric arc furnace, and ignoring the supporting infrastructure that is required, such as the electrical grid connection, gas pipelines, balance of the plant, plus all the non-physical scopes, such as regulatory approvals and workforce training. And this can lead to a huge scope creep, and that also will lead to a creep in the cost of the project and require additional funding. Shareholder, stakeholder risk is another issue. Many of the projects are going to be first-of-a-kind technology. They're complex and to implement, and this is generating time, cost, and performance risks, the magnitude of which the customers want borne by the equipment suppliers and the contractors. However, the equipment suppliers and contractors may resist this as they have no experience in managing such risks. They've also learned that the steel industry pays more attention in achieving positive project outcomes if they have some skin or some dollars in the game. So this can lead to overpriced bids and contractual disputes. Another one is technology risk. New technologies need to develop through a series of technology readiness levels, or TRLs. If the process of moving from a small-scale pilot installation to a large-scale commercial operation is rushed, then we have unexpected operational issues which can emerge, and this can lead to disappointing performance outcomes and the need for system redesign. Now, the graph that we have here, where's my pointer gone? Here we go. This is actually the development history for a process called FINEX. And I used this because recently there was a claim of a 15-year development cycle for the FINEX process, which is the blue here, basically. But in actuality, if you look back to the beginning of its history, we're looking at more than 80-odd years. So the question becomes, are we going to be able to achieve reality in the timeline that we're looking at from now till 2070? There's also an issue that some of the viable technologies will never be acceptable to the steel industry or the operations because of incompatibility. And hence, we really need a significant amount of oversight to improve true opportunities for sustainable steelmaking. Another big issue that's arisen since COVID is the procurement risks, also aided and abetted by some of the recent tariffs. Project implementation timelines can be delayed due to failure to appreciate that some of the equipment has long lead times. An example is transformers and compressors can have a lead time these days of up to 2 years, which means orders need to be placed before even potentially the contracts are signed for the new equipment. Additionally, some of the issues arise from moving forward with the DRI solution would be build rates, or for any. We're going to need huge amounts of green energy, which aren't achievable, huge amounts of hydrogen, again, sustained from the renewable energy, and also the number of electric arc furnaces that are due to be built in order to maintain the steel tonnage. Implementation risks. Not only are many of these projects complex systems in themselves, but they also often need to be integrated into a current steel mill. And this generates business-critical risks relating to maintaining the operation of the plant whilst installing this new equipment. And performance risks is a big issue too. The new technologies often need extended testing, and commissioning periods to optimize performance of the system before full operation can commence. And during this period, subsequent operations, unexpected performance issues can emerge that require change to the system design. Oh, here we go. The last two in this category are the high CapEx and OpEx estimates and risks. Obviously, not only are many of these projects complex systems, but they are also costing hundreds of millions, if not billions of dollars to build. This is making it challenging to create a robust business case for investors to be confident in. And also the profitability of these investments can be significantly impacted if the costs of operating, excuse me, have been underestimated, or as we're seeing currently, there's unexpected volatility in the utility costs in order to run the projects. Come on. There we go. Sorry about the lag in the slide motion. Some of the examples down here, this chart shows the example of ArcelorMittal, who's the second largest steelmaker in the world. And basically 4 out of these 5 projects enumerated here have either stopped, been postponed, been abandoned, or delayed for a significant amount of time. The one that now is going ahead is the one in France, in Dunkirk. They've just announced the restart of that project. The second point is access to electrical power. Insufficient, excuse me, insufficient short-term access to required low-cost renewable energy is obvious. You can see from the chart over here on the right-hand side, the target for 2030 is over 11 terawatts, and currently 2024, we were only producing about 4.5 terawatts. And you can see from the graph, the yellow here is the solar energy. It's predominant in the new energy capacity that's coming online. But that is also going to depend on location. And the lack of renewable energy is going to make it difficult to obtain the quantities required as we convert to electrification for either electric arc furnaces or other systems, and obtaining that from the grid. There are high costs and complexities in terms of building large solar, wind, or even nuclear SMRs as power systems. And also you've got to consider their associated battery storage and distribution networks that would need to be close to the steel mills. In terms of increasing power demand, of course, that shift to electrification and competition for power, green or current, is going to increase and drive up costs. And this is going to make it even harder for the steel makers to secure energy that they need at a viable plant. And I've put in some statistics there. The prices mapped around the world range from $0.11 US per kilowatt to over $6.41 per kilowatt hour. And when you consider hydrogen is somewhere between, inefficiently, between 52 and 65, 66 kilowatts per kilogram of hydrogen, it has a significant impact on where sustainable steelmaking is going to occur. Number 3 is the different and changing government, environmental, and trade policies between the regions. Many of our steelmakers today are international. They have a global presence, so government policies in different regions have a significant impact on making a comparative assessment between investment options. And all these policies have been seen and can change partway through a project, which generates risks in terms of business viability. The fourth one is lack of harmonization of this carbon accounting system. Without standardized carbon accounting, it's difficult to compare the performance and demonstrate any progress that's occurring. And this, of course, can complicate reporting and undermine the stakeholder confidence. I put in a little table at the bottom there that shows the difference between annual carbon footprint per capita and historical. And if you look at the annual CO2 per tons produced, the Chinese, of course, at 54% of the world's steel, are way ahead of the US in second place. If you start to look at per capita, of course, then US is high because its population is way less than the Asian nations. And historically, if you look at the generation of CO2 greenhouse gases, the US is way out ahead because we've been tracking it since 1750, and we were ahead of the game in terms of the Industrial Revolution. Number 5, as Mike alluded, we need for high quality steel, clean, segregated, high quality and low cost feedstock for the electric arc furnaces. And I've put in some examples here of different charge materials. And I think you can see from the scrap piles that it's not exactly totally segregated, and it's certainly not very clean. DRI and HBI on the right-hand side, on the other hand, is. But if we don't have good quality charge material, it can restrict production, increase costs, and impact the viability of a project. And apart from the cheap natural gas being a viable option for DRI production, Argentina, for example, has a low availability of good scrap. So a lot of their steel is produced based on up to 100% of DRI in the electric arc furnaces. Another big issue is this limited market demand for premium priced green steel. The mills really require 200 to 300 euros to validate the expense of the projects, and they may concede 20 to 30 euros of that. But the clients appear only to be prepared to pay 100 to 150 euros per ton for the green steel. And obviously, this pricing barrier or premium pricing barrier is going to challenge widespread adoption of green steel ultimately. And the last point I'd like to make is the lack of implemented commercial scale and practical carbon capture, use, and sequestration systems. This graph on the right-hand side has come from the International Energy Authority. The link is there. Basically, it is showing in 2025, only 0.03% of the greenhouse gases were captured. And it's estimated that only 2.4% will be captured by 2030. And the graph shows, if you blow it up, that the steel sector is the smallest sector that's being addressed currently. They've been underperforming elsewhere. Carbon-free hydrogen is required to stabilize the CO2. And of course, sequestration requires caverns that are semi-reactive to bind the CO2, and those are not available everywhere throughout the world. So CCUs being the be-all and end-all of the excess CO2 that's not taken care of from the electrification and the hydrogen decarbonization solutions still remains to be a question mark for the future. And with that, I'll pass it back to David, and thank you for your attention.
Thanks, Sarah and Ian, for a great presentation. So now we know that an industry that's already fighting instability and cycles in its product pricing and its raw materials and electrical pricing now has to go and spend billions with all the challenges that involves. So our final section will, after all of this, what does the future look like? So our final section was prepared by Chris Pistorius, Joe Morey and Brian Black, Ian Sutherland and Rick McKinnon. It'll talk about what does the future look like in the different regions. Go ahead, Chris, please.
All right, thank you very much. Given the sobering context that Sarah outlined, I do want to outline some of the existing possibilities which are already implemented and close to implementation, and some that are a bit further out to decarbonize both ironmaking and steelmaking. And as you see, I shall talk about existing technologies, scope for improving those and increasing their implementation. Some of the newer electricity-based technologies, at least one of which is probably a year out from being demonstrated on industrial scale, and then a few others that are at large pilot scale. And I shall reference the very nice document that the AIST produced under a NIST grant that can give you a lot more detail about this. And then I shall circle back to some of the challenges that Sarah mentioned and use, I think, a very useful, sane way of analyzing these that Hatch has distributed for several of the projects. So first, talking about the blast furnace, the technology is already highly optimized because coke, the main source of CO2 in the process, is an expensive input. So historically, there has been a real drive to decrease the coke rate. But there are things we can do to get that even lower. So some of the things that are already done is to partially replace the coke with other fuels, which typically are injected through the tuyers. Highly established approaches are to use pulverized coal. That doesn't really change the carbon intensity, but injecting natural gas and coke oven gas can decrease the carbon intensity a little bit. And then the ultimate aim possibly is to use much more hydrogen. It's a little bit limited in terms of the amount of the that you can actually inject without upsetting the temperature balance in the furnace. Something that has much more scope, I think, is something that's done already, which is to change from feeding iron ore to partially feeding scrap or other sources of iron, reverts. And the numbers are, as you see, for every 10% of the iron that's in metallic form, the coke rate drops by 7%. And there is a productivity increase, which allows some companies to close smaller, arguably less efficient blast furnaces and use a bigger furnace with iron input to run at a higher productivity. And then there are some piloted approaches. There historically have been some large-scale pilots in Europe under the ULCOS program to look at top gas recycling, and there is a current instance of that technology which is about to be trialed in India, essentially the blue blast furnace, where similar to what is done with gas-based direct reduction, the top gas is recycled to give each carbon and hydrogen atom the maximum possibility to grab oxygen from the iron ore. This requires substantial changes. You cannot run on air, you need to run on oxygen or highly oxygen-enriched input gas. And typically there is some requirement to preheat this gas, of course, as it goes into the furnace, and that's then different than the existing stove approach. And then, as Sarah mentioned, carbon capture has been piloted, hasn't been implemented at a large scale, but still has some scope from a cost point of view. It seems attractive, although in the absence of a large-scale demonstration, one doesn't really know what the true cost will be. The other existing technology that already reduces the carbon footprint of iron making by about half compared with blast furnace BOF operations is gas-based direct reduction. That is well established. We saw the production numbers earlier. And if you add in the consumption at the electric arc furnace, the total intensity per ton of crude steel is about half that of the blast furnace. This excludes some of the Scope 3 emissions from pelletizing. And there is the option to transition from natural gas to hydrogen. It is not a big change to the process. This has been piloted at large scale quite successfully under the hybrid program in Sweden especially. And the first major plant using pure hydrogen produced on site will be Stegra in Sweden, expected to start up parts of their operation later this year already. One of the potential issues with using more and more direct reduced iron in steelmaking is the quality of the feed. The gangue is not removed in the iron making process if you're doing direct reduction because it's all in a solid state. This is in contrast with the blast furnace that melts everything. So the impurities are taken out as a slag. So the gangue is removed as a slag, but in the later steelmaking step in the electric arc furnace. And there are existing operations that run on 100% DRI, no problem. But if the gangue content increases, that slag volume can become problematic. And the current idea is to use a different melting unit, a so-called electric smelting furnace, which is kind of mimics the lower part of the blast furnace, using electrical energy to produce something like hot metal and slag, which can be used in cement production, and then use that iron either in an electric arc furnace or in a classic basic oxygen furnace. And then in terms of steelmaking, electric furnace steelmaking is of course a very well-established technology. It is older than BOF steelmaking by half a century. It's been around a long time. It's used to make 70% of the steel in the US. And because we mostly remelt iron, inherently the energy intensity is much lower than that of the iron making processes. So it comes out to be around 400 kilowatt hours per ton of steel. Scrap quality is really important, especially tramp elements like copper, tin, and nickel build up in the scrap pool as we keep on recycling the steel. So for some steel grades, this matters less. Others are very sensitive to copper and tin, especially. So one does need a source of clean iron to dilute the impurities. Ultimately, one needs to combine this with a source of low carbon electricity to have both low Scope 1 and Scope 2 emissions. And that can then get this number of 300 kilograms down to essentially zero, depending on what sources of carbon one uses in the electric arc furnace. So as a summary of what one can achieve with the existing technologies, there are plants that do this already that are running profitably, except for the last one, which will be running soon. So it's compared with a baseline BF blast furnace BOF around, depending on what one includes, 1,500 kilograms of CO2 per ton of steel. If one maximizes natural gas injection, you can decrease that a little bit. In part, that is because one needs more oxygen enrichment, and producing oxygen isn't necessarily carbon-free. If you charge the maximal amount of metallic iron you can do, you can see that really decreases the CO2 emissions substantially. This includes the CO2 emissions from making DRI in using natural gas. The DRI EAF one, again, there are plans doing this currently. That's around 900. If you use renewable electricity, one cuts out around 140 kilograms. If you use scrap, we're at around 300. If you use renewable electricity, again, you have that approximately. And ultimately, if one uses hydrogen DRI in an EAF with biocarbon and renewable electricity, it's very close to zero. There's a little bit of carbon for arguably carburization of the material needed. So these are using existing technology and a tweak on existing technology in the last case. There is a real spectrum of possibilities available. And just to emphasize, I'm sorry, that this is real. This is the Rocky Mountains steel mills in Pueblo, Colorado. What you see in the front is the 300 megawatt photovoltaic solar plant that produces the power to make this around 1.1 million tons of steel per year. And there are a couple more examples of this going up around the US. Not all of them have the production exactly next to the plant, but use renewable electricity. So in my last 10 minutes, I'll talk a little bit about some of the new technologies, where they are, and what their typical numbers are. So the first of these is the tweak on the existing technology, which uses hydrogen instead of natural gas in direct reduction. There's high temperature electrolysis as an option. Also low temperature electrolysis, both of these are being piloted. And as a context to this, just some numbers about how low can we expect the energy requirement to go for any of these processes. The important number here is the baseline number, which is what energy do we need to break the bonds between iron and oxygen in our raw material, which is typically Fe2O3 or hematite. All of these processes, ultimately, if you draw a boundary around the whole plant, you get hematite in, you get iron out, and you get oxygen as a byproduct. So this reaction is what is being done in all three of these electricity-based examples. So we need to provide at least that energy, and that turns out to be around 2 megawatt hours per ton of iron. So 2,000 kilowatt hours per ton of iron, about 5 times what we use in an electric arc furnace. And as we shall see, when we add in the other things we need around the plant, the typical number ends up around twice this, 4,000 kilowatt hours per ton of metallic iron, or roughly per ton of crude steel. So it will require a large amount of electricity, as Sarah pointed out. So here is one such an instance. This is very roughly the hybrid or Stegra type processes, where we use hydrogen to make DRI, which is then ideally transferred hot to an electric arc furnace, or if it's higher gang material, an electric smelter furnace to make crude steel. And the numbers, as I show in the top right, add up to around 4 megawatt hours per ton of crude steel. Where those numbers come from are what you need to produce the hydrogen. I have a slightly more optimistic number than Sarah's, but it's somewhere 50 to 60 kilowatt hours per kilogram of hydrogen. Of course, we need stoichiometrically around 55 kilograms of hydrogen. So if you multiply those two numbers, you're already over 2.5 megawatt hours per ton. And then you substantial electricity requirement is to preheat the gas, because this is how we get the energy for the reduction reactions and to heat up the product. And then we need the normal steelmaking number. So if you add all of these together, they are close to 4 megawatt hours per ton of crude steel. So that's a combination of existing processes about to be industrialized, so very high on the technological readiness level. The other two that I'll mention are not as far along, but are being piloted at large scale. So the high temperature one is the one developed by Boston Metal, which feeds ore into a bath of slag, which is also the electrolyte in the process, and then produces iron at the cathode. This has been very well demonstrated at lab scale and at large pilot scale. The crucial part of this technology is the inert anode, which, at least in the published documents, is a high chromium with a bit of iron alloy, which has really unusual properties to help it withstand the conditions. And that's really of course, the innovative part of the process, and the only part that doesn't strongly rely on existing technology. The electricity supply will be like aluminum electrolysis. The refining after tapping will be normal ladle metallurgy, well established. And the refractory for this vessel will take normal refractories, because one can tweak the slag to both balance the electricity, the electricity conduction through it, as well as the compatibility between the slag and the refractory. If you add up all the numbers with no heat losses, the total is around 3 megawatt hours per ton. So it makes sense that the total will be around 4. There are a couple of low temperature processes that I'll briefly mention. There's one that was developed as part of the European ULCOS program, Siderwin, which runs at modest temperatures, 100 degrees Celsius, very alkaline solution. The iron stays solid. So interestingly, this is a solid state reduction process where the iron grows as these dendritic growths into the existing iron oxide. So any gangue, of course, will be kept in the material. And it's run at numbers like 2.6 megawatt hours per ton of iron at large lab scale. And this is about to be demonstrated in a plant called Volteron that is due to start next year. The alternative process developed here in the US is the one of Electra, which dissolves the feed material in acid, so somewhat classic hydrometallurgy, and then uses large-scale electrolysis to produce cathodic iron, which then is a very clean feed material that can be used in normal electric furnace steelmaking. In fact, it's a good material for specialty steels as well. Again, it's being run at large pilot scale and being scaled up soon. So all of these, the numbers add up to around 4 megawatt hours per ton. And just to emphasize that we need clean electricity for this to make any sense at all. It needs to be essentially zero carbon electricity. Because if we take the US average CO2 intensity, of course, it varies with season, but around 360, 370 kilograms of CO2 per megawatt hour. If you multiply those two numbers, then we are back at 1.5 tons of CO2 per ton of steel. If we just connected one of these plants to normal grid electricity, we would be back at a blast furnace. So we really do need large amounts of very low carbon electricity at low cost. So that will undoubtedly be a challenge. In closing, just some perspective on the challenges and the opportunities. I will direct you to this document put out by the AIST. And this is the AIST NIST roadmap published last year that got a lot of opinions from the industry, and I think gives a very nice balanced view on what the possibilities are. And it presents what it got from the industry in a number of ways. One of them are these challenges with implementing these solutions. Availability of low carbon electricity, of hydrogen, or quality requirements. And then how ready are these technologies? So just one graph from this report is this one that shows the amount of CO2 that one can save relative to the baseline of blast furnace BOF steelmaking. So in this context, bigger is better. And then the x-axis is the year at which respondents to the survey reckoned this could be ready. So the bars indicate the range from the earliest to the latest year of the estimate, and the numbers in the circles indicate the actual average year. As you can see, opinions really vary, and the amount that one can save really varies as well. But if we just take hydrogen-based DRI, the estimate is a little bit after 2028. If Stegra commissions their plant as expected, actually this lower end of the bar will need to be extended downwards. But some of these you can see do go out to very far in the future. So this is just a snapshot. Definitely the document is useful to look at in more detail. So just one additional point, which is the framework that Hatch developed, which is, I think, very useful to understand what makes for a successful implementation. So these are the so-called McNulty curves. So what is plotted here is the percentage of the design capacity of the plant that was achieved up to about 4 years from startup. And these different series refer to specific characteristics of these processes. So if you're in series 5, you never get there, and series 4, it gets to some kind of steady state, but it's less than the design capacity, which of course has huge cost implications. So I'll let you look at these later, but basically series 1, you need many things to be correct at the same time. It needs to be a relatively mature technology. You need good piloting. You need to understand your raw materials very well. And basically one flaw drops you to the lower series, where you basically take much longer to start up the plant, bleeding money as you go, and maybe not ever reaching capacity. So this is a theoretical framework developed based on a large number of actual plants, and these include pyrometallurgical plants. Some of them were minerals processing plants. So this is a series of nickel laterite smelters, and you can see these real plants varied from series 1 to series 4 in reality. And the big difference here was how mature the technology was and how much piloting was done. So Sarah already mentioned some of these points. Hatch formulated this in terms of a very specific context of electric furnaces, and again, same points of being sure this is technology that is ready, and we are moving forward with that there's good piloting, and that all the peripherals are understood well. So I'll close on this slide of what we can do, and as we transition to questions, I'll let you look at these, but there are a number of things that we can do. One of these is thank you for being here, for understanding these technologies better, but also having a nuanced understanding of what is available and what can be done as we move our industry to where we definitely need to be, which is a much lower carbon intensity where we are currently. So thank you. And with that, we can transition to questions. David.
Thank you very much, Chris, and your team for that last presentation. It's to everybody else, it's been a high level, broad-based review of our industry compared to the very detailed deep drilling that we've had in previous webinars. But what's become apparent is it's very complex, and if you want to succeed in business, manage the cash. So we have 10 minutes for questions. I'd like to start the first one with Sarah. Oh, before we start on the Q&A, could you make sure that you go do the poll, please, so that we can do the analysis and then we can share the results afterwards. So Sarah, all presentations mentioned green electricity, and when we compare the old integrated plants, which used the carbon it generated in the gases to make electricity, it was actually pretty self-sufficient in terms of electricity, but it had a ton of carbon on the back end. And you compare that to the EAF mills, which cannot self-generate any electricity unless they have a solar plant next door. What do you think is the horizon for green electricity around the world? Because different regions have different timelines.
Yeah, I think around the world the solutions are going to be a little bit different. You've got MENA, who's got a lot of solar potential because of the power that the hours of sunlight that they have down there. I think in the United States we're probably going to end up with SMRs, nucleus, individual small ones per plant is going to be more likely. It's going to be more efficient to have one on site than try and hook into the grids. Wind is becoming a bit of an issue around the world. Actually, you say that you can't generate electricity from the electric arc furnace plants. They are now looking at so doing. Originally, they said that they could not because it was a batch process, and if the furnace is down, there's no power. But in the situation now where they've got productivity running crazy and often two furnaces into the plant, it's now being looked at as a potential source of some of the electricity that's in there. But it's definitely going to vary from around the world, just as the iron making is going to vary because, the Asian countries have put in a lot of new blast furnaces and are continuing to do so because they don't have the support for the power. And in the West, we're tending more towards the electrification. It's going to be very different for every area in the country and world.
Thank you. Ian, we were talking about electricity again, and we're not the only industry that wants cheap green energy. The data farms and electrifications of the vehicles, etc., is also putting pressure on the demand. How do we stand in the steel industry in terms of being able to afford to pay for this green energy relative to data farms?
Yeah, very good question. I think at the end of the day, affordability has to be seen as, part of the overall production cost. The affordability of purchasing green electricity, is part of the operating costs, which gets factored into the overall, price that the steel is going to, be charged at. And therefore, I don't think we should necessarily just, focus on that as being sort of a major issue. But, having said that, the increase in supply of renewable energy is a question that dominates so many different heavy industrial sectors right now, and power that can be generated as a sort of using natural gas as a sort of bridge towards longer term, sources of cleaner electricity. And Sarah mentioned nuclear, and whether that's small modular reactors or larger reactors, that will definitely be part of the equation in the future. And then you've got just the trajectory of the costs of renewable energy itself. If you look at the trajectory of solar PV systems over the last 20 years, the reduction of the price of electricity produced through solar is just dramatically reduced. So I feel confident that the solutions are emerging for the steel sector.
Thank you, Ian. I did notice in Chris's presentation that the solar farm alongside the mini mill was for 1 million tonnes per year. And if we compare that to a blast furnace BOF plant making 4 million tonnes of steel a year, that's going to be a very different scale. So I have a question for Joe. Joe, if we get the green electricity and we get it cheap, we're still going to have carbon emissions. How is the world standing on carbon capture, utilization, and storage?
Yeah, that's a very good question. There's a few cases of carbon storage coming out. Most notably, the one, the joint project between Exxon and Nucor over in Louisiana is a carbon storage, so it's a very natural fit for them. And Carbon Free is as one group that's out there that's looking at carbon capture and utilization, their mineralization of CO2 in calcium carbonates. So those are two that are out there, but it's a very burgeoning industry. We'll just say it like that. There's a lot of work that needs to be done.
Thank you. So, Chris, you showed us the timelines of the new technologies coming through, and the world is evolving very, very quickly. From 2010, we wanted to be close to net zero by 2030 and then at it by 2050. And as this graph showed, we're still producing more CO2 than ever. Should we be reevaluating the timelines in terms of what we're looking at in carbon tax costs and what's realistic plans to be spending billions? Do we have to reevaluate everything?
Yeah, absolutely. All of that is being reevaluated all the time, as we saw in Sarah's summary of some projects that have been either cancelled or substantially delayed. And yeah, and these are trillions of investment. A very modest estimate is maybe $1,000 per ton of annual capacity for just an iron making unit. A 2 million ton per year natural gas DRI facility would cost you around $1 billion now, depending on where it's being built. So these are really large investments for equipment that is designed to last a really long time. To be fair, the estimates for 2030 were maybe 20% reduction in emissions based on a baseline from several years ago. And actually, several big producers are essentially there. And that is by optimizing the existing operations, some of the possibilities that I had shown. Most of the big steel producers are still committed to net zero by 2050, but it is becoming clear that this is really hard. It is going to be more expensive. And the way to get there while maintaining economically sustainable production, that is not clear. Whether it will take universal carbon tax, government interventions, customers being willing to pay more for steel, probably some combination of those. But yeah, you're absolutely right. This is all being re-evaluated all the time.
Question, thank you. Question for Mike. Mike, we're seeing the blast furnace BOF and the EAF sort of becoming a hybrid process, trying to improve the quality of the iron, reduce the carbon, and the arc furnace is now as much a smelter as it is a melter. How do we see that going in different regions of the world?
Well, the different regions of the world have different rules, and let's step back a little bit. If we look at the fact, as Chris pointed out, it's €1 billion or dollars for a new DRI plant, and that DRI plant requires natural gas, and they got to rebuild it anyway. Are they really going to build it in a place like Europe? And so if they're going to rebuild it anyway, DRI is transportable, so they can build it somewhere else and bring it to be used in the electric arc furnace. Now, the blast furnace will not likely go away in my lifetime. They're still building blast furnaces. The question is, can they mitigate the CO2 emissions through some of the measures? Hydrogen has very limited effects for reducing CO2 emissions, maybe a maximum 20% that you can inject for technical reasons. You can't go much more than that. And then DRI, hydrogen-based DRI, Sarah and Chris talked about the enormous amounts of green electricity that's required. So in terms of the electric arc furnace being used as a smelter, it is already. And that's primarily for cleaner steels. DRI is diluting the impurities of scrap. But that DRI could come from anywhere in the world. And the question is, if you're going to rebuild your whole steel plant, you're going to put it in places where the regulations are more friendly, and where the raw materials, the natural gas, and or if it ever gets to hydrogen, the hydrogen is quite cheap. But that's all I can say, because there's still too many things that are unknown, and the industry cannot exist on subsidies. It has to pay for itself without subsidies, because you have many other industries competing with the steel industry for the subsidized dollar or euro.
Thank you for that. So we've come to the end of the time, but we will take the questions that are still outstanding and answer them one way. Madison, could we ask you to share the results of the poll and then close things off?
Yeah, absolutely. There's the poll results for everybody to see. So it's a pretty even split for the top three: energy use and efficiency in steel production at 24%. Cost and competitiveness of more sustainable steel, 24% also, and greenhouse gas emissions from the steelmaking process at 21%.
Thank you. What's interesting is that as a subcommittee of the Energy and Utilities Committee, the decarbonisation team has been, apart from looking at the new technologies that Chris went through, is how do we improve the energy use and efficiency of our existing plants. And I think we're going to have some training workshops set up around that to focus on that in this fall and next year. The greenhouse gas emissions, yeah, the guys have, and Sarah talked about how each of the different process paths can improve itself. But the big challenge is not just within what we make, but within the raw materials industry, which is also undergoing some generational change as the quality of the raw materials they produce, the quality of the iron ore needed for DRI, for example, is all becoming a challenge. Essentially, the customers won't pay more, and yet the costs everywhere are going up. And that's operational costs. And apart from the capital investments that Chris explained, we have to borrow that money, and we've got to make enough cash from operations to pay off the interest and all those loans, apart from whatever subsidies the governments may be handing out. So thank you for the poll. Madison, could we ask you to close things off?
Yeah, thank you all so much for attending the webinar today. And thank you to our moderators and content contributors who put a boatload of work into putting this content together for you all. Really hope that you got a lot out of it. Just a reminder, this will be available for you to view after the close of this presentation. It'll be on AIST's website. And also upcoming, we have 2 more webinars planned for the spring. So we'll have one for March 19th and one for April 2nd, focusing on hydrogen in the steelmaking process. So those registration links will be out soon. We have many webinars up on the website. Those can be found either in conferences and expositions or through the technology committees tab. And then don't forget to look for our other upcoming trainings, as well as AIST Tech 2026 in Pittsburgh. So everybody get excited. We hope to see you there. Again, I want to thank you all for joining us, and thank you to our presenters and content contributors and moderators. Really appreciate you all, and hope you have a great rest of your day. Thank you.